All right. Hello. Am I audible? You can hear me?
Yes, sir.
Right. Amazing. So just before this, we had our AS class, and this is just for the people who are taking that AS class. The meeting ended before we could finish everything, and so there's the issue of this fixed timing is still there, and the class even started late. The meeting had been already started, but people joined late. So still working on that, and apart from that, in Pakistan over here it's 8 p.m. and so I understand if for me also it's the end of the day, and this is A2 class is the last class, and so it gets kind of tiring and all. So what I'm doing is we'll probably change the timing. Hopefully the timing will be changed tomorrow. Let me share my screen as well before, so we can also start quickly. This is, we have, right. So you can see my screen. It's visible. Is the screen visible? Okay, perfect. So yeah, about the timings, I was thinking to move this. Let me see if yeah. So what I was thinking is to move the timing from for A2 physics. Let me talk about A2 physics. We'd probably move it to from 5:45. Sorry, my mistake. From 5 p.m. to 5:45 p.m. Is there anyone who is in the class right now? Is there any problem? This is Pakistan time. Is there any problem with this timing?
Sir, I don't know the chemistry timings yet, but they were told to be from 5:30.
Chemistry A2?
Yes, sir.
Okay, so if there is a clash, I checked with the timetable. There was at the time there was no clash in with A2 chemistry. I'm not sure, but I'll check it. So if there is any clash, I'll let you know. Yeah, I'll communicate that in the group, right? So I'll communicate the timings, the new timings, whichever they are. We'll check around. We'll see that if there is no clash, and so we'll change the timings. The only problem is I think it gets a bit too late around this time. Even I'm drained of my energy. I'm sure that probably you people are drained as well. But so let's see. So this is just maybe we might change to this timing. You'll be notified before the next class anyway. So that's that. Let's come back to so is there any question in from the previous class? Any question from what we did yesterday? Right, so I'll assume that there is no question. So then we're discussing tangential and linear velocity at the time. So I think that's what we did. The last thing was discussing this thing. So is the concept of tangential velocity clear? All right, so I'm guessing it is clear. Then we discussed this point that the angular velocity is going to remain same throughout the circular motion for the body that is in this circular motion. So at this point, it is moving with some angular velocity omega. At this point, it will also have that same angular velocity omega, right? However, the linear velocity, if I increase the radius of my string, then the linear velocity changes. Essentially, basically, it increases, right? Okay, so now a body that is moving in a circle at a constant speed changes velocity. Why? Well, because velocity is not just a magnitude, it's not just a number, it also includes direction. So when a body is moving in a circle, at one point its direction is, you can let me draw a circle, and I think it's pretty obvious, right? So at this point, that the direction, if it's moving in this angle, its direction is this. If it comes to this point, its direction is this. And so it keeps changing its direction if it's moving in a circle, right? So that's pretty obvious. And hence the speed is not constant. It's the velocity is changing because the direction is changing, and hence it's always experiencing acceleration. Is this point clear? I guess it's pretty straightforward. So because it's changing a direction, there will be some acceleration experienced, and we'll look at that acceleration. It's known as a rotational acceleration or a centripetal acceleration, right? And if there is some acceleration, then because of F equals ma, there will be some change. There will be a force being exerted on it, and that is the force that we call a centripetal force. It's not really a force. Centripetal force, it's not really actually a force. It's just something that is trying to keep the body towards the center, move towards the center, right? Okay, so are you aware of this expression that force is the rate of change of momentum? So it's a change in momentum, time rate of change of momentum. So you can see this expression because we know that momentum is defined as mv and F is ma. But what is A? A is V over T. So I can put in place of A, I can put V over T. So this becomes mv, which is momentum P, and then you have T. So if there is some acceleration on the object, then its momentum is also changing. Right? Okay. So centripetal acceleration is given by this expression. It's A is equal to R omega squared, where omega is the angular velocity of the body, and R is the radius from this body to the center of the circle. And it's also can be written in terms of the tangential velocity. So this V is the tangential velocity using this one, because we know that using this expression, if you can see it clearly, let me get rid of these circles. So this is V equals R omega. You can use this expression to write down your centripetal acceleration in terms of tangential velocity. So is there any question up until this point?
No, sir.
Okay, so because I think that we are moving a bit slow, so I'm just trying to go over some things which are not so hard to understand. I'm trying to go over them quickly, but if you think that that is causing some problems, you can let me know, right? So if again, my point is that if at any point you have a question in your mind while I'm going through things, you can just stop me and ask me, right? So now, because we have something that is the centripetal acceleration, you can define centripetal force using the same thing that I explained, this same concept, because F equals ma. So just multiply a mass with this acceleration and you can work out for force, right? And so the force is F equals m times r omega squared, where r omega squared was this acceleration. And similarly, you can use the tangential velocity representation of the acceleration, and you can write down v square over r in place of a over here. And so you get the centripetal force as this. Now, again, this is the same point that I was stressing about, that centripetal force, it is a resultant of all of the forces that act on the system in circular motion. So it's not just a particular force that is trying to make the object, or it's not really a force that is forcing your object to move in a circle. It is just, as you can see, it is just center seeking. So it seeks to keep your object towards the center of the circle. Is by this expression, as you can see. And then there's a statement, think about it. If you know that a person in a satellite, when it is orbiting Earth, they experience weightlessness. I'm sure that you're familiar with this phenomena, right?
Sir, can you explain the phenomena?
The phenomena of weightlessness, right?
Yes, sir.
Okay, so basically what happens is when you're orbiting, you're constantly falling towards the Earth, right? But what happens is that you're orbiting the Earth, so you're moving with some velocity, and because you maintain that velocity, that's why you're not falling to the Earth, right? But
Okay, sir.
but yeah, but what's happening is you are indeed you are continuously falling towards the Earth. So have you ever felt when I don't know if you, hopefully you have not felt it, but what happens when if an elevator was moving and suddenly this thing that was keeping the elevator, it ruptured or it broke or something, what would happen to the person who is inside the elevator?
Sir, for a little time he would float.
Yeah. So basically he's falling he's still falling down, but with him this elevator is falling down as well. Right?
Yes, sir.
So what is happening is that the weight of this person is in this direction, but what happens when the string breaks? The effect of this weight or the effect of the gravity is eliminated by the forces that are resulting from, for example, if you consider this case, the case of this Earth and a satellite orbiting the Earth, it would be eliminated by the resulting forces from the orbital motion. So it is just that the what do you call that? The gravitational force appears to cancel out, and hence you experience as though that there is no weight, but that's not really the case. Is that okay?
Yes, sir.
Okay, so that's this. Now I have also prepared some questions. Let's move on to those questions. The problem is I'd really like the timing to be shifted, because for me it's too late right now and I'm exhausted at this point. So hopefully from tomorrow the timings will be different. They'll be more towards the afternoon, somewhere around about that, because this thing, it's very exhausting like this at this time. Hopefully none of you will have any issue with the time. If that's okay, then I would really like the timings to be a bit early. Is that okay with everyone present in the class right now?
Yes, sir, but only the issue of chemistry class.
Clash should not be there, right?
Yes.
Yeah. So yeah, of course. So keeping that in mind, hopefully there is some slot where we can make this a bit early. Can you just tell me about your schedule, about the classes that you're taking?
Right now, the chemistry classes are not happening, and I'm taking physics and chemistry.
You're taking physics and chemistry. Okay. Amazing. So I'll keep that in mind, and I'll arrange the timetable accordingly. Okay, let me open this. Okay, I think it's here. Let me share the screen once again. You can see my screen now.
Yes, sir.
All right. So here are some problems. Let me just zoom it in. So these are the first problem is very basic. Let's start. We have this thing that we have to convert the following angles into radians. And so I'll just do one or two, and then I'll send you this worksheet, and you can attempt the rest by yourself as well, right? So because the pattern is the same to solve all of these parts. So we have to convert angles to radians. He should have mentioned from degrees, right? So because all of these angles are over here in degrees. So the relationship between a degree and a radian is defined as pi radians is equal to 180 degrees. So there's no problem with this, right? Okay, so you'll just use that 180 degrees is just pi radians. What about 90 degrees? So if pi radians is 180 degrees, then 90
Pi upon 2,
degrees.
sir.
Yeah, exactly. So because you'd get 90 by dividing 180 by 2. So you'd divide both sides by 2, you'd get pi by 2. And similarly, how would you get 60? 60 would be? Okay, so it would be 60 multiplied by
1 upon 3.
2 pi. Yeah, exactly. So 2 pi by 360. So that would be pi upon 3 radians. And similarly, for 45, it would be pi by 4. So I think this is very easy. Nothing, no rocket science over here. Similarly, you can convert these angles into degrees using the same relationship over here. We have pi by 4. Pi by 4, luckily we just did it over here. So we know that it's 45 degrees, right? So you'll just write 45 degrees, 2 pi by 3. So what you do is you'd have 2 pi by 3 into 360 by 2 pi, or you can say 180 by pi, right? So
120.
pi goes, yeah, exactly. So it would be 120 degrees. And 1 radian would be how many degrees?
180.
That's no, yeah, it would not be 180. Think about it. We had pi radians as 180, right? So, but this is 1 radian. Well, pi is it's a never-ending number. It's 3.142 blah 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 blah. But it's this thing, right? It's not 1. So you'll have to do the conversion by simply 1 multiplied by 180 by pi, 180 degrees by pi radians, right? And so this would give you, well, there is a radian over here as well. So this radian goes away, and this is just 180 by pi. So if I were to do this, it would give me 57.3 degrees. Yeah, exactly. So actually this was interesting. 1 radians is 57.3 degrees. All right. So well, these were very easy. Let's look at this question. Question number 2, and it says that you have a car which is traveling around a circular bend of radius 24 meters at a constant speed of 15 meters per second. So the situation is something like this, that there is a car. Now, hopefully you'll not judge my drawing. This is a circular bend. Let's just use this. And there's a car which is traveling on the circular bend in this direction, let's suppose. And this circular bend has a radius from some center, it's 24 meters, and it's moving at a constant speed. V is equal to, now look at the units for the speed. It's meters per seconds. So this has to be a tangential speed, right? So V is equal to 15 meters per second. Did you get that point? Why did I not write omega equals 15? Because omega is not meters per second, right? Omega is the angular velocity, which is measured as radians per second, right? So these are the units for omega. It's because it's the angular velocity, right? As we discussed in the notes. I think we did that in the last class.
Sir, it would be degree per second.
Yeah, it can be degree per seconds, it can be radians per second. So any unit that is associated with angle. Similarly, as how kilometers per hour, meters per second, these are all units for velocity, right? Tangential velocity. Similarly, for angular velocity, it could be radians per seconds, it could be degrees per seconds, it could be there's another unit called gradient per seconds as well, and so on, right? So the point is that you get this. Why did I write tangential velocity as 15 meters per second? So that's clear, right?
Yes, sir.
Okay, so then they're just asking you to compute the angular velocity of the car, which is extremely simple because we know radius, we know the value of r, we know v. What is something that connects v, r, and angular velocity, which is omega? So we have omega, we have v, we have r. Just quickly think about an expression which connected all of these three. Can you tell me right now, from what we did in the in the theory part of this chapter?
Sir, R V square upon T.
R v square upon
Time.
Time. And you're saying that this would give me omega?
No, sir, it was.
It's okay, no problem. But yeah, but you can check that, right? You can also check these things by using dimensional analysis, which just means that you can check the dimensions on both sides. If the dimensions match, then you're good to go. But if they don't match, then there's a problem with an expression. So if you look at this expression, you can see that there is v squared, which means meters per second squared. And then you have r, which would mean 1 meters. And then you have time, which is seconds. So this would just give you meter cube over second squared divided by second. So this thing goes. So this gives me something like meter cube per second. But these units don't work out with omega, right? So these units don't work with omega. We know omega is what? Omega is radians per second. And I need a relationship between omega, v, and r. So think about this. What about this expression? V is equal to r times omega.
Sir, wasn't this the linear velocity?
Yeah, exactly. So this part is linear velocity. You're absolutely correct. But what I can do is, I know r, I know linear velocity. I need to compute this. So I'll just rearrange this. I'll just take r to the left. So I'll get v over r as omega. Now I can put the values of v and r in this expression. and evaluate my omega, which is the angular velocity. So is that clear?
Yes, sir.
Okay, perfect. So in place of V, we have 15 meters per second. So I'll just put that in, 15 meters per second. R is 24 meters. So let's just put that here. And then we have this meters, meters cancel out. You're left with 15 upon 24. It's 0.
0.6.
Yeah, 0.64. Okay, 0.64 per second, right? So you can write now, you can put radians per second. So that's your angular velocity, which you were asked to compute. So that's what you had to do in this problem. And we're done. So is there any question regarding this problem?
No, sir. Sir, can you
should
share the?
share these notes?
Yes, sir.
Yeah, of course. I'll share these notes after the class is over. By night time, or hopefully, but by tomorrow you will have these notes, right? So the real question at this point is, did you understand why I did what I just did?
Yes, sir.
Okay, perfect. So then okay, so let's move on to, okay, so now this is hell of a problem. It's very simple. It might look as if it's not, but it's pretty simple. So let's read it first of all. We have the diagram shows a racing car rounding a bend of a radius 120 meters. So we are given a radius of the bend and on a banked track traveling at 32 meters per second. So the track is banked at some angle. That's what a banked basically means, that it is inclined at some angle, right? And this angle is phi. And we're also given the, yes, sorry?
Sir, can you label what would be 120?
Oh, you mean the radius, this thing you're talking about, the radius of the bend?
Yes, sir. Can you label it on the diagram?
Oh, yes, of course. So think about this. It's traveling in a circular path. On this diagram, it's not really, so think of a circular track. You have a track that is circular, and if something is bend on that circular track, what would the radius r be? It would be okay, so it's something like this thing is going to move in a circle, right? So and it's going to, so I'll have to draw something like this. Let's get rid of this thing. And so it would look something like this. You know that racing tracks are designed in this circular form, right? And so the car starts from here, it will go like this, and when it comes back to this point, one lap is completed.
Yes, sir.
Right? So exactly in the same way, it's moving along this path, and but this path is banked at some angle. So from the center of the car to the center of the track, that's the radius r. You have to picture it in your head, and if you can do that, that would be very nice. But if not, I'll try to elaborate a bit more. But is it okay? Is it okay, or it's not?
It's okay, sir.
Okay, perfect. So that's your radius, and it's traveling at this speed, 32 meters per second. So that's what speed would that be?
So the angular
Tangential,
velocity.
or it would be tangential, right? Can you take some time and think about it? Why would it be the tangential velocity? Think in terms of the units. That's always very helpful. So tangential is something, it means linear velocity. Linear velocity is always measured in these type of units, right? Meters per second, kilometers per hour, and these type of units are used for tangential velocity, because it's not an angular velocity, but angular velocity, the name says it that it has to involve the units of angle. So it should be either radians per second, degrees per second, and something like that, right? But you can see the units over here, they do not involve any sort of angle. There's no radians, there is no degrees, nothing like that. It's just meters per second. Meters is a tangential thing. Hence, so these are the units for tangential velocity. Does that make things clear? Any better?
Yes, sir. Yes.
Okay, perfect. So always look at the units, and if you know your units, it's very easy to recognize what is what, basically. So I'll just give you an example over here. Sometimes I don't remember. I find very hard to remember or memorize formulas, expressions, and everything. So if I don't remember some expression very correctly, I'll just check the units on the left hand side of the expression and on the right hand side of the expression. If they match, that means my guess is correct. If they don't match, that means there is some problem. So it's always nice to know your units. You can it saves you a lot of times, basically. So let's get back to the problem. A part, they're asking you to calculate the angle phi if there is no tendency for the car to move either up or down the track. What does this mean? This means that the car is not allowed to move up on this track or slide down on this track. It will not do that. It will just stay in this position, and it will keep moving in this position only. So the car is not moving either to the left, or it's not moving either to the right on the track. Is that point clear?
Yes, sir.
Okay, so now they're saying you may treat the car as point object. Well, you do that all the time when you're doing any calculations. You treat your objects are always treated as point objects, because if you don't, then you have to involve then your calculation gets really messy. So we treat things as point objects. So anyways, so
Sir,
yeah.
what does point object mean?
Oh, it just means well, there is no such thing as a point in real life. In mathematics, we define point as something that has no distance or no no size. Point object is just whenever you're doing physics, think about this. If you have this car, there will be some weight coming from the tires, there will be some weight coming from the person who's sitting in the car, right? And there will be some weight coming from the bumper, the front bumper of the car as well, the back bumper, then the seats, then so we don't say that, we don't include all of those things separately. We just treat it as a point mass. So we say that this whole thing it's like a point, and it has a weight, and that weight is the entire weight of the car, which you can, by adding all these weights from the tires, from the chairs, from the by chairs I mean the seats in the car, the steering wheel, the bumper, all of those things, right? They'd be contributing to weight. So we don't treat them we don't treat them separately. We treat them as a point mass, and we say that everything is concentrated on this point, and this point then has some weight or mass, which is weight is pointing in the downward direction. And yeah, so is that clear? Does that make this point clear?
Yes.
Okay, perfect. So before I proceed, can you let me know how much time is left in
4
this
minutes
meeting?
and 40 seconds.
4 minutes and 40 seconds. Let's try to solve this problem in that time. There's still this problem of time, the fixed timing on this Zoom. They're telling me that it will be fixed very soon. So let's hope that tomorrow it's fixed, right? And so we'll not have this issue as well. Okay, so right, so you may treat the car as a point object. So let's try to solve this part A first. Calculate the angle. So we have to compute this angle phi. Now, to do that, you are familiar with resolving force or force vectors into components, right? So for example, if you have a force vector that is pointing like this, and your coordinate system is defined as this, where this is your vertical axis, let's call it y, this is your horizontal axis, then a force vector in this coordinate system, for example, it's like this, it would have some component along this direction, and it would have some component along this direction as well. Sorry, this would be fx, right? Do you understand this thing, or should I go into detail of
No,
this?
sir, I understand.
Right? Yeah, so okay, amazing. So basically you have a force that's pointing like this. So how could it point like this? Your coordinate system is telling you that there are two independent directions. One is up and one is right. Now every other direction that we can make out of this up and this right in this specific figure, right? In this specific coordinate system. So we can make this now, but this vector is a combination of up and right. And similarly, how I made this force, F vector, it's a combination of this up and this right. So this up and right, these are basically how much contribution is in this up direction is the Fy component. How much contribution is in the right direction is the Fx component. So anyways, you said you understood it. I, for some reason, I went on into it anyways. But okay, so if you look at this diagram, they have given you this diagram. They have resolved the forces as well for you. So if this is the angle phi, then this is the cos component of this vector r. R is the resultant force, right? And this is the sine component of this vector r. So then you can do this thing. You can say, by the way, when they said that the car is not moving either on the up of this track or below, sliding down the track, they meant that the car is basically in equilibrium. So that means that the sum of all the vertical components of the force should be 0, and sum of all the horizontal components of the force should be 0. So let's try to solve this vertical components. So we have r cos phi and m times g. These are the only two vertical components in this entire diagram. Would you agree with that? Hello?
Yes, sir.
Okay, yeah. Would you agree with this, that there are only two vertical components in this entire diagram, r cos phi and w equals m times g?
Yes, sir.
Yeah, so there is no other component that is in the vertical direction, right? So that means r cos phi is pointing up, so I'll take it plus r cos phi. And w equals mg, it's pointing down. So if I take up direction as positive, that means that my down direction is negative. Now this thing is a complete choice. You can pick one. You can say that you could have even taken up as negative and down as positive. But whichever you choose before you start your problem, you have to like, stick